We talked about one of the applications in the last discussion. Uh, let me just there are of course a few other applications which I would like to do, but before I uh, before I do that, let me just say that the entire quantum statistical mechanics is also like an application of grand canonical answer. So let me just make a beginning. We will come back to some of classical applications of grand canonical ensemble and do them later. But let's go and look at quantum statistics. So here we are going to talk about. So one of the important things that I will consider is that we are always going to consider non-interacting, non-interacting. Okay. So one of the advantage of non-interacting system is that you can use something called so in this case we can use single particle energy. For example, let's say that let's say there are n particles. N particles, and these particles are non-interacting. Are non-interacting. So now let me set the representation. So let's say that I have particle 1 and I have certain energy levels for particle 1. There are infinitely many energy levels. And particle 2, and that has got certain energy levels. There are also infinitely many. And particle 3, it has its own energy levels. And we obtain these energy levels by solving the quantum mechanical problem. And like that, I have some n particle which has its own energy. Okay, so these are what we call as single particle energy states. Now, if there is no interaction between them, the energy levels of one particle will be same as that of the energy levels of the other particle. For example, if you consider, let's say, n particles in a box of volume E, then we have these energy levels as you can call it as n1, n2, 3, which is equal to h bar square I square into n1 square plus n2 square plus n3 square divided by twice n v to the power. So these are the energy levels of particle in a box because these particles are non-interacting. Each of the particles has the same set of energy levels. Now we have something called occupation number representation. Occupation number representation. So this representation is what we will use to develop formalism in quantum statistics. And what is this representation? Let's say I have epsilon 0, epsilon 1, epsilon 2, etc. These are my energy levels. How many of them? There can be infinitely many of them. And let's say there are n0 number of them. N0 of the particles are in the ground state, and N1 of the particles are in the first excited state, and 2 of them. And these numbers are called occupation numbers. And once these numbers are fixed, that means this particular number, we define it as one particular mode. Okay? But there is a constraint on this. The constraints are straightforward constraints, and the constraints are sum over j, nj should be equal to total number, and sum over j, nj times epsilon j is equal to the average energy of the particle. Now these are the two constraints that the occupation numbers have to satisfy.
Sir,
Yeah.
sir, for photon gas, this doesn't satisfy, no?
Hmm?
For photon gas,
Yeah, right now I am keeping it very general. Photon gas will specialize it later.
okay, sir.
So this is a general thing. So now what happens is that suppose if you are interested in writing down a kind of a grand canonical partition function. Okay, so suppose we have, let's say, for a given configuration of, of a mode that is given nj. Okay, so this total energy is given by this. Total energy is given by this, and total number of particles are given by this. So we have energy E and number of particles N. Okay. So now suppose if you are interested in writing down the grand canonical partition function, so we can write grand canonical partition function. So let me write this as q times q of beta v comma the fugacity z as sum over n is equal to 0 to infinity z to the power n into, of course, the canonical partition function, because that is what we have in terms of so that is essentially canonical partition function of n. But canonical partition function for n number of particles can be written in the following fashion. So this is equal to sum over n is equal to 0 to infinity x to the power n. And now I have to take sum over all these possible modes. That means a kind of a over set, and this sum is constrained uh, by the constraint that sum over j nj is equal to n. This is the constraint. And then I have e to the power minus beta into the energy. Energy is n0 epsilon 0 plus n1 epsilon 1, etc. So this is the canonical partition function. Okay, so this is something which we have to evaluate. Now, this constrained summation can be made into an unconstrained summation. Okay, so note the following result. Note that suppose if I have sum over n is equal to 0 to infinity and sum over, let's say, n1 comma n2, sum over n1 comma n2 with a constraint that n1 plus n2 is equal to n into some x to the power n1 into y to the power n2. Let's say I have some summation like this. Now this can be written as sum over n1 is equal to 0 to infinity x to the power n1. This is an unconstrained sum over n1, and sum over n2 is equal to 0 to infinity y to the power n. Both are unconstrained sum. So this is something that can be written. Now it is not very difficult to realize this. For example, let's try to evaluate left hand side. So if you take n is equal to 0 and n1 and n2 has to be equal to 0. Okay, so let's take n is equal to 0. Then the summation will have only 1. Suppose if you take n is equal to 1, n1 can be 0 and n2 can be 1, or n2 can be 1 and n1 can be 0. That means you can have terms like x plus y. And now if you take n is equal to 2, then you will have x square plus y square plus x times y, and so on. So left hand side is going to be something like this: 1 plus x plus y plus x square plus xy plus y square, and so on. This is what is going to be. That is, next you will have all cubic terms. That is x cube, x square y, xy square, y cube, and so on. Now look at right hand side. Right hand side is something like this: 1 plus x square, etc. A product of this with 1 plus y square. So look at first few terms, that is 1 plus x plus y plus x square plus x y plus y square. So you can see that term by term, this uh, left hand side and right hand side are going to be same. So that way you can verify that this constraint sum on the left hand side can be written as a product of unconstrained summations. And this can be written even if you have more than two indices. So this tells us that okay, this is basically 1 plus x y x square y square. So if you understand this mathematical equation, then the grand partition function now can be written as. Note that so we have this grand partition function with z is equal to. I can write down this n is equal to 0 to infinity. This capital N is n1 plus n2 plus n3, right? That is z of n0 plus n1 plus etc. into sum over these nj's, and with a constraint that sum over j nj equals n into e to the minus beta of n0 epsilon 0 plus n1 epsilon 1 plus etc. Now this can be now written by using the above mathematical equality. This can be written as sum over n1 is equal to n0 is equal to 0 to infinity e to the minus beta epsilon 0 into z raised to the power n. So this is one term. Then I write the product sum over n1 is equal to 0 to infinity z e to the minus beta epsilon 1 raised to the power n, and so on. I will have infinitely many such terms, but for every energy level there is one term. Now this can be written in a shorthand notation like this. It is called product. This is a symbol for product over J. Sum over Nj is equal to 0 to infinity Z e to the minus beta epsilon J raised to the power N. So this is the expression for Q beta T grand canonical partition function for a system of non-interacting particles. Now you can see that this particular equation, you can see that this epsilon j. What are these epsilon j? These are single particle energy levels. Energy is associated with the single particle energy level. Okay, and your so this expression up to this we have been quite general. Now we cannot be general henceforth. We have to ask a question: what kind of is particle? What kind of particle? So in quantum statistics, Based on the nature of particles, you have two distinct statistics. Okay, so if you have fermions, these are um, particles with half integral spin, half integral spin. Then they their total wave function, their wave function must be anti-symmetric upon exchange any pair of particles. This implies particles obey what is called Pauli's exclusion principle. Pauli's exclusion principle. This means for any single particle energy state, the occupation number can be 0 or 1 and nothing else. This is a very important statement because this is what happens. This is what very distinguishing feature of Fermions. So, which implies that I can write down the grand partition function for Fermi-Dirac statistics, the three statistics, as a function of beta, E, and Z, as product over K, product over J. Now, this Nj for every epsilon j, this Nj can be simply 0 or 1. So that means it is empty or it is occupied with one particle. That's all. So that tells you if Nj is equal to 0, I have 1. If Nj is equal to 1, I have Z into e to the minus theta. So this is the grand canonical partition function for Fermions. We have Fermi-Dirac states. Now, on the other hand, you have bosons, particles whose spins are integrals, particles with integral spin, and where the wave function, is 0 or 1. must be symmetric upon exchange exchange of any pair of. So there is no restriction because of the symmetric nature of the exchange. So there is no restriction. So no restriction on the occupancy of a single particle energy. No restriction on the single particle energy. That means the occupation numbers, that means your Nj is equal to 0, 1, 2, etc. Can go up to infinity for every value for both Einstein epsilon j plus e to the minus beta epsilon j the square and so on. And that is how I have and uh, product so to so these are the statistics that you. In fact, the particles will get divided into these two categories. Namely, uh, there is a relation. So this relation between spin of the particle, spin of the constituent particles, and statistics they obey goes by the name spin statistics connection. Initially, this was supposed to have been given by Pauli, But this can be proved, this can be elevated to the status of a theorem called spin statistics theorem, and can be proved using the tools of quantum field. I just wanted to make this remark so that you can keep it in mind if you ever study quantum field theory. You can keep this in mind and search for it. But we are not going to look at it as a spin statistics theorem. I want you to understand that there is a connection between the spin of the particles and the statistics theory, and that connection is what I have made here. The grand partition function different for different particles, whether they are fermions or bosons, and the entire physics of the systems is also different because statistics. But notice that this is all because of the nature of overlap of these wave functions is different based on their spins. So once we have this grand partition functions, now you can ask, you can try many things. For example, first let's look at single particle energy state average occupants. Which you can write it as average number of particles, NJ of. So this you can obtain by asking what is the average number of particles. So for that we find average number, average number. And this we can find because we know once we have grand partition function or the average number. So we know that average number of particles obtained from the grand partition function by taking z dou by dou z of lambda. Okay, so let us look at Fermi-Dirac statistics, FD statistics. Okay. In the case of FD statistics, your average n is equal to z dou by dou z. When I take logarithm, the product will become sum. Correct? So that is sum over j logarithm of 1 plus z e to the minus theta epsilon. Okay, so that is my grand partition. So now I can take this, do this term by term. Somehow a 1 by 1 plus z e to the minus epsilon j, and the derivative of this term is e to the minus e to the minus beta epsilon. So this can be written as sum over j z into e to the minus beta epsilon j divided by 1 plus z into e to the minus beta epsilon. So it is sometimes useful to write it in the following fashion. So we take this numerator to the denominator and then write this n as uh, sum over a. We write this as z to the minus 1 into epsilon a. Okay. So which I could have written it as sum over j of average number of particles in each of this. Okay. So if I write it like that, then I have the average occupancy of a single particle energy state Nj, which is given by 1 divided by z to the minus 1. So this is an expression for average occupancy of a permitted occupancy. Now let's look at case of Bose-Einstein statistics. Let's say I have EE states. If you have B and your average n is equal to z, so by the z of so you have a minus sign, and I have sum over I logarithm of 1 minus z into e to the minus beta, because that is 1 by 1 minus z e to the minus beta j. When I take logarithm, I get a minus sign out. So that is what. So this also you have, you can do a similar thing. Then you will have sum over j z e to the minus beta epsilon j divided by 1 minus z e to the minus beta epsilon. So once again, I can take this numerator to the denominator and then write this n average number as sum over j 1 by z inverse e to the power beta epsilon j minus 1, which if I write it as sum over j nj. Then you have average occupancy for a single particle state in terms of Bose-Einstein is equal to 1 by z inverse e to the power beta epsilon j minus. Now there is also interesting. It will be interesting to see what happens if these are classical particles. So classical particles, that means classical particles, they obey what we already know as Maxwell-Boltzmann statistics. Boltzmann statistics. Okay, so we will try to look at Maxwell-Boltzmann statistics in the same occupation number representation. Now, what happens is so if you have classical particles, that means let us look at MB statistics in this occupation number representation. So if you go back to your expression of that is for a given mode of this nj, there are factorial n divided by product over j factorial nj microstates. Okay, so these many microstates are there, and for indistinguishability, we divide this by factorial n. So if you do this, then what happens is your Q, Maxwell-Boltzmann of beta v, right, is going to be equal to sum over n is equal to 0 to infinity, get to the n, and sum over we have this sum over this nj, and with a constraint that sum over j nj is equal to factor n. Now you have 1 by product over j nj factorial, okay, and this capital N factorial will be cancelling because we are dividing by capital N factorial into e to the minus beta sum over j epsilon j n. So if you use that result, then you can write this as product over j and sum over nj is equal to 0 to infinity z e to the minus beta epsilon j to the power nj divided by factorial n. This is what we will have, because there is a product over nj is sitting for each of the term. You write that nj factorial, and this is what we will have. But this summation is well known. So this is nothing but you have product over j exponential of z e to the minus beta. So this is e power x is x power n by n factorial, n is equal to 0 to infinity. So the grand canonical partition function for Maxwell-Boltzmann statistics is beta v z is equal to product over j single particle energy levels, exponential of z e to the minus beta epsilon. And suppose if you are interested in finding out average number of particles, again it's z rho by rho z. The product becomes sum, and logarithm of this is simply z into e to the minus beta. Logarithm exponential will cancel, and you have this simply gives you that this is sum over j z e to the minus beta. And if you are writing this as sum over the nj, so the average occupancy of a Maxwell-Boltzmann under Maxwell-Boltzmann statistics is simply z into e to the minus beta. So we have expressions for average occupancy of single particle energy levels in the case of three different statistics: classical statistics, which is what is called Maxwell-Boltzmann statistics, and quantum statistics, Fermi-Dirac statistics, and Bose-Einstein. Now, looking at these expressions, it is suppose if so let epsilon be a single particle energy, single particle energy of an energy state, and let average n epsilon be its average occupancy.
Sir,
Yeah.
sir, in classical system, isn't the particle distinguishable? You can track every particle.
Yeah. So in classical system, we have there is some indistinguishability at the level of permutation of this particle, just like what we discussed in the case of Gibbs paradox. So I am dividing this as that factorial n to take care of that kind of an indistinguishability.
Okay, sir.
Whereas in quantum statistics, actually there is no, they are identical. That means you don't this kind of counting. That is why I did not put any weight when I did quantum statistics. Okay. Anyway, we will. So this I am going to write it as 1 by z to the minus 1 into e to the beta epsilon, and I'm going to call it as plus some a. And I'm going to say that this a is equal to plus 1 for Fermi-Dirac statistics, FT statistics. And this is minus 1 for Bose-Einstein statistics. And this is 0 for Maxwell-Boltzmann. Okay, it's easy to remember one. So this is a unified expression where there is a constant a that is changing, other things are all same. So for Fermi-Dirac statistics, a is plus 1 for Bose-Einstein statistics. A is -1, and for Maxwell-Boltzmann statistics, it is equal to 0. So this is average occupancy. Now the average occupancy also has an important, for example, consider, let's say, consider the case of FD steps. Okay, so if you consider the case of FD statistics, you know this average occupancy is given by 1 by Z inverse e to the beta epsilon plus 1. Now, your single particle level, let's say this is the energy level. There are two possible states. That is, when you take, you have n epsilon. Now, this n epsilon can be 0. Okay, so if you have n epsilon to be 0, then the energy of that energy is 0. Or you can have a possibility that n epsilon is equal to 1. In which case the energy is epsilon. Okay, so that means I have it is like I have two microstates. Okay, so I have two microstates. Of these energies 0 and epsilon. It is like two level system now. Correct? It is like two level system. Now, suppose if I am asking a question that what is the grand partition function for this? So let me call that as some Q. So the grand partition function for this is it is like Z into e to the minus beta epsilon. Okay, this is your Gibbs factor, this to the power 0 plus Z into e to the minus beta epsilon, this to the power 1. So that means that is equal to 1 plus Z into e to the minus beta epsilon. Okay, this is your grand partition. Now you can ask a question that what is the probability that the energy level is occupied. What is the probability that the energy level is occupied? That means the probability that your n epsilon is equal to 1. That means it is occupied. That is equal to Z into e to the minus beta epsilon. This is the Gibbs factor divided by Q. So which is equal to Z into e to the minus beta epsilon divided by 1 plus Z into e to the minus beta epsilon. So I take this numerator to denominator, then I have Z inverse e to the beta epsilon, which is same as average occupancy. So that means the average occupancy is same as the probability of the occupancy. Okay, so the probability of the occupancy is same as that of the energy of the. Okay, so this is something which you have probably seen in when you do electrons in metals in solid state physics, that you consider this probability and you say that at t equal to 0, this probability is 1 up to Fermi energy and 0 beyond Fermi energy. So this is the expression which you use to find out uh, various properties of electron shear method. So this is the use of average occupancy. Now remember that we have been continuously talking about single particle energy levels, and that is possible because we are able to uh, get to do that because we are using a non-interacting system. So this is the expression for average occupancy of each one. Now look at this expression. Even though it is buried like this z, what is our z? Our z is namely the fugacity, which is given by e to the power beta. Okay, this is fugacity, and mu is your chemical potential. Okay, so if you are explicitly writing that, then your probability of n epsilon, let me put it this way, your n epsilon, average n epsilon, in terms of this one, you can write it as e to the power z inverse. Okay, z inverse is e to the minus beta mu. So I have e to the power beta into epsilon minus mu plus a, and a is equal to plus 1 for FB and minus 1 for BE, 0 M. Okay, so this is what is in terms of. Now, supposing if you are interested in asking what are the possible values, suppose let us denote beta times epsilon minus mu, beta times epsilon minus mu, let's call it as some x. Okay. And then your average number of epsilon becomes 1 by e to the x plus a. Okay, so now supposing if I want to ask what is the value that your x can take. Okay, so for example, let's look at Fermi-Dirac statistics, FD statistics. Okay, and if you look at FD statistics, and then let's say that so FD statistics, you have average number is equal to 1 by e to the x plus 1. Now at x equal to 0, your average n epsilon is half. Right? And as x tends to infinity, then average number of epsilon goes to 0. And as x tends to minus infinity, then average number of particles will go to 1. Okay. So this is the behavior of this function. So if you are trying to plot this function of x, let's say, let's look at x versus this average number. So you can see, let's say this is let's say 1, and this is let's say half. So you can see that it goes to 0, and then it goes to 1 as x goes to, and it will go through this half. It may not go so fast to 1, but this is how your Fermi-Dirac function. Now let's look at Bose-Einstein statistics. Bose-Einstein statistics, your average number in terms of this x is 1 by e to the x. If x equal to 0, sorry, this is minus. So x equal to 0 implies this n epsilon goes to infinity. Okay. Now, if x is negative, then average n epsilon is also negative. But this is unphysical. This is unphysical because the average number of particles occupying can be 0 or positive. It cannot be negative. So this is unphysical. That means x less than 0 is not allowed. Okay, so x less than 0 is unphysical. Okay, so what happens if x goes to infinity? As x goes to plus infinity, and x goes to plus infinity, that means this n epsilon goes to 0. Okay. So that means the range of this x is only between 0 less than or x and less than infinity. This is the range. Whereas in this particular case, the range of x is minus infinity less than x less than plus. So if you are interested in looking at how this looks like on the same graph, so you can see that it go to infinity as x goes to 0, and then it at some point it will merge with this one and then goes to 0. So this will be what you call as Bose-Einstein. Okay, and what is your Maxwell-Boltzmann statistics? Maxwell-Boltzmann statistics is simple. So Maxwell-Boltzmann statistics that corresponds to a equal to 0. So your average n epsilon is simply z into, okay, it is simply e to the minus. So e to the minus x is something which you can draw. For example, so you can see it will come to 1 here, and then it is exponentially decaying. Then in this region it just goes on. So this is your MD. So MD statistics also don't have. So MD statistics also has a relation that minus infinity less than x less than infinity. Okay. So if you see, this Bose-Einstein statistics has got a restriction in terms of the range of this x, and this restriction is it has a very important physical relevance. Okay, so if you look at x, carefully, x is nothing but epsilon minus mu by ABT. Okay, so x has to be greater than or equal to 0. This implies your epsilon has to be greater than or equal to mu. Okay, epsilon has to be greater than or equal to mu. What does that mean? That means if you are, let's say that if you have so if you have ground state, for example, if the ground state is 0, okay, so if ground state is 0, ground state is 0, let's say epsilon is equal to 0, then it has to be equal to mu. That implies your mu is also equal to 0. Okay, what does that mean? If mu is equal to 0, that means there is no cost in adding more particles to that energy state. So this has very important implication for bosons. Okay, so we will discuss that when we are discussing Bose systems. But just notice that the minus sign that is sitting there, that A is equal to -1, makes a huge difference in terms of bosons and fermions. So that plus and minus sign is what makes kind of a very huge difference. Okay, so this is as far as the occupancy numbers are concerned. Now we can talk about general, for example, one of the important things in any system is to talk about equation of state. Equation of state. So the basic idea is same thing like what we discussed when we talked about grand canonical. So we have this, we have Q for Ft as product over J 1 plus Z e to the minus, or I can simply write it in the new language, product over epsilon into 1 plus Z into beta. This is product over all single particle product over single particle energy. And this implies I can write down your PV by kBT as logarithm of Q. Somehow single particle energy levels, logarithm of 1 plus Z e to the minus beta. Okay, so this is let's say equation 1, and then we have equation 2, namely the n, the average number of particles, is sum over epsilon 1 by Z inverse e to the beta epsilon plus 1. This is equation 2. Okay, so I can state it easily. Okay, so we can state eliminate Z between equations 1 and 2 to get the equation of state. Okay, so as long as I don't have to find the equation of state, I can make this statement. But finding the equation of state by doing this elimination of Z is not very easy, because it is it's not very easy because this has sum over all possible states. These are so many terms. In fact, infinite sums on both sides. So what one generally does is that you try to, for example, so it's not easy. So please understand that it's not easy to do this. So one can do one concept can do this approximately right. Doing this approximately is some equation finite of that, say up to the power 4 or something like that. And then solve for that in terms of average n, and substitute that solution in equation 1. Then you will get an equation of state which is so this is a procedure, and the same procedure can be used for finding the equation of state of Bose-Einstein statistics also. So this is something which, but when we did ideal gas using using the Grand Canonical ensemble, I demonstrated ideal gas by eliminating Z. Z can be eliminated very easily in that. Whereas in a general case like this, elimination of Z is not that easy. One has, in fact, people try to do this using Mathematica kind of software, where you can invert one relation, find Z as a function of n, and substitute that state. Okay. So we have, and then get expressions that are approximate. Kind of almost completed the foundation for the quantum statistical mechanics. Now we have to see what are the things that we are going to do in quantum statistics. So as I told you that we have two types of statistics, namely Bose-Einstein statistics. Okay, so in Bose-Einstein statistics, we are going to look at uh, the work of Bose work on thermodynamics. This is works developed into functional Bose. So we'll try to understand how his idea of in fact the issue of identical particles, which now learn as a consequence of the symmetric properties of the wave function, was introduced in a very innovative way into the statistics by Bose even before the wave function itself was discovered. So we will look at the work of Bose in terms of thermal radiation, and let us also try to do it in some detail so that we get a hand of the essential insights into the work. And the second application that we will look at is what is called Bose-Einstein condensation. This is an important feature of bosons, which happens for particles with finite mass. And Bose-Einstein condensation is macroscopic occupancy of a single particle ground state at temperatures. So this is something which is very unique to bosons, and Bose-Einstein condensation will be our next story. And the third application is we were talking about specific heat of uh, uh, solids. So so we will do these three things for sure, and if there is time, then we will try to look at superfluid helium. And certain excitations of superfluid helium, but I will just keep it with some question. Not very sure if we can reach. If we are able to do it quickly, then we can. And then let's go to FD statistics. In FD statistics, we have. So we will first talk about electrons in metals. And we discuss various physical properties, such as specific heat of electrons. Classically, they are supposed to be temperature independent. Experiments showed that it scales linearly with the temperature, and we show that use of thermodynamic statistics brings that feature back in compared to Drude-Lorentz theory in classical physics. Then we have two theories of magnetism. It's called Pauli theory of paramagnetism. Pauli theory of paramagnetism. Then there is Landau theory of diamagnetism. Landau theory of diamagnetism. And then we have an application that is quite different from what we have seen so far. Namely, we will talk about stability of white dwarf stars. This is also an application of stability of white dwarfs. So this work is initially was done by Chandrasekhar, and we see how, as an application of Fermi-Dirac statistics, the Chandrasekhar limit can be derived. So these are the applications of Fermi-Dirac statistics. So this are the topics that we will cover in this unit as an application of our quantum statistics. Okay, I will stop here and there are questions.
Sir,
Yeah.
sir, are you going to study more applications of grand canonical partition function, like
Yes.
apart from the quantum one?
Yeah. So I'm going to do two applications. Okay. So in grand canonical ensemble. So there are going to be two applications. One is in terms of chemical reactions, based on how actually you are going to calculate rate of chemical reactions from the grand canonical partition function. So this is one application. The second application is it is also related to this, but it is also related to some biological. This is a single application. I will so biological phenomena. So with respect to one or two phenomena of biological sciences, I will try to show how using grand canonical ensemble one can. So these are the two applications which I will do. Essentially, I will demonstrate this with some representative examples. Okay, so these
Sir,
two,
yes, sir.
yeah, so these two will require one class. So I think one class I can finish in 30